Okay, so I think I'm gonna go ahead and start. They just say start whenever. My name is Kathy. I am from the Ethereum Foundation. In particularly, we have a team that works on all the ZK stuff, so privacy or roll-ups, we all work on that. And for myself, I actually work on what we call ZKML, so zero knowledge machine learning. So that's what I was supposed to be talking about today, but I also realized that not everyone has a background in ZKP, so we will also do a little bit of intro before we dive into ZKML. Right, so just a little bit background about me. You will have that in a bit as well. So I am not a cryptographer, so don't worry. I won't be talking about all the mathematics and stuff. In fact, I'm more of an applied ZKP engineer. So I only do the applied side, the application. And that's because I came from a background of data science. So I am a machine learning engineer for many years. I built models, train models, etc. So that's my expertise. And right now I'm working to basically put ZK into machine learning. Right, so just to begin with is what is ZKP? So you might have heard about it a lot in a lot of L2 roll-ups, but today the main focus is not roll-up. So in essence, on blockchain, what we usually do is what's called non-interactive ZKP. The idea is that you have a person called a prover and a person called a verifier. So the prover will generate something like, for example, to prove that I am above 18 years old, okay? And then this prover will send a proof, a ZKP, to the verifier, who will then verify the result. So he will get a true or false from that proof. Okay, so that's just an essence. Right, so basically the prover has some mathematical statement, and then he has to work to convince that the statement is true. Okay, so that verifier, we say verifier, and we put a person here, but in reality, this could be just a smart contract. Okay, so that could be a smart contract that basically is called the verifier contract. And then we put it on chain. Whenever we submit like a bunch of numbers, which is a mathematical statement to that verifier contract, then we get a true or false statement, a true or false outcome based on that contract. Okay, so more complicatedly, so with the following properties. So what is ZKP really? We use ZKP for 4 different reasons. The first 2 I will explain in a bit. The third one is what usually people think about is zero knowledge, right? So we don't know anything about the actual underlying information. And the fourth thing is actually not an official property of ZKP, but we often use it. Okay, so let me explain them one by one. Okay, so completeness and soundness sound pretty dumb. The name sounds very fancy, but if you think about it, it's pretty dumb, okay? So essentially, it's saying that, okay, this proof is valid. So if the prover is honest, so if we have a valid proof, the verifier should eventually say that this proof is true. Okay, so it's just kind of a mathematical thing. Very obvious, but that's just how one of the properties should be. And then the other property is basically soundness, saying that the verifier will not say something is true unless it's actually true, okay? So it will not verify false statement, essentially. Okay, so you can think of this as like no false negative and no false positive, essentially. Okay, so that's 2 just mathematical statements. The third one is more important. The third one is, other than the fact that the statement is true, the person does not know anything other than that. Okay, so for example, I have my age on my decentralized ID. Okay, I want to prove that I'm above 18 years old. All the verifier is going to get is only the fact that I'm above 18 years old. Nothing else, okay? So nothing about what the actual number is. It's not going to know that I am, for example, 30 or 40 or 50. Just the fact that it's above 18. So that's what we mean by zero knowledge. So except the thing that I want to prove to you, nothing else is exposed. Okay, so that's the first thing. And then the last thing is actually quite important, and that's why you might have heard of like ZK rollup, like ZK sync, scroll, Starknet, etc., etc. You often heard that it's ZK rollup, but I want to make sure that you don't misunderstood is that most of the ZK rollup is not ZK. Okay, most of the ZK rollup use the fact that it's succinct, meaning the size of the proof is actually much smaller than the actual computation being done. Okay, so that's why the rollup works. So you have a L2 chain, you try to compress the information and then commit it to L1. Okay, this is what rollup means. And there's nothing private about rollup, okay? So that's why it uses the fourth one, which is sassiness, or you can think of it as compression. Okay, so like zipping a file, if that makes it easier to understand. Okay, so that's the 4 properties of ZKP. That's as theoretical we will get into. Next up, we will talk about some application. Before we talk about application, I just want to show you how formally it is done. Okay, it's okay if you don't understand this graph yet, but just a more complicated version of what is actually being done is, you have a prover, a verifier. So the prover will take some inputs and also a key. We'll talk about that in a little bit. And then it will output some proof and some public output to send to the verifier, where the verifier will say, okay, yes, this is a valid proof, or no, it's not a valid proof. Okay, so that's just a kind of a more complicated version of how it is actually done. But don't worry about that, because we'll look into some applications instead. Okay, so why ZKP with blockchain? So ZKP is not something new. Actually, it has been around for many years, but it has some very good properties that can be used with blockchain. In particular, so I assume we all know about the blockchain already, right? With blockchain having 2 problems. One is the limited block size. In particular, not only limited block size, also limited contract size. If you have written Solidity contract, you might realize there's only 24 kilobytes that can happen on the smart contract, right? At least for EVM. Okay, so 24 kilobytes. Also, the block size is limited. The other thing is the transactions are totally transparent. Okay, so that's 2 big problems for people coming from Web 2 or people coming from Web 2, right? So we are not used to having transparent transaction. We're not used to having limited block size. Well, what ZKP can offer as a solution here is 2 things. So first of all, it can compress. So that's the 4th property we talk about, sassiness. So we can compress some of the computation into a proof, and then it can be proof on the blockchain. So that means the computation is done off-chain, but then we just submit a proof of what we have done correctly onto the blockchain. Okay, so that's the first thing. The second thing is that we can also prove some ownership or data while maintaining privacy, right? So let's go with the transparent point. Usually it's transparent. How do we not have transparency? Is to have some privacy and then just use a ZKP to prove something. Okay, so to put it more concretely, well, actually, I will skip this for now. So what we do is we will focus on something called a circuit for ZK snarks. Okay, so this is something that you will see, which is just one system. So you can think of that as there's 2 versions of ZK proof that you can construct. One is snark. The other one is stark, as in StarkNet. So we'll just do ZK snarks for this talk, and whatever ZK snark stands for is not important there. Okay, so, well, what is a circuit? A circuit is something that you might have seen in your, perhaps like electronic engineering class or something like that. Basically, it's a circuit, okay? It's really what you think of as an electronic circuit where you have some gates and stuff. So unfortunately, nowadays, if you're writing ZKP, you have to write something that is a circuit. Okay, so it's not a Turing complete program. It's not the same as if you're writing JavaScript or TypeScript. It has a lot of functionality that does not exist in JavaScript or TypeScript. Okay, so this is the reality right now. But later, there are a lot of companies already working on something called a ZKVM. Okay, and the idea is once there is ZKVM, then you can just write ordinary programs and make it ZK. Okay, but that is not realized yet. So we still have to write some kind of circuit that does like some gates like plus or addition or multiplication, etc. in order to get like what we have to do. So the disadvantage is that you need to write a custom one for every single kind of computation that is being done. Okay, so let's say if I want to write a circuit for a model to classify pictures, I have to write a custom circuit. If I have to write another one that does maybe like proof of membership, I have to write a new circuit. Okay, so that's a disadvantage. But then again, we're only focusing on this part today. Okay, so let's start with something that is more, I guess, practical. Okay, so now we're done with the theory part basically. Let's go into the practical part of kind of writing a ZK app in Accents. Okay, so a lot of time people think that I want to hide something, so I need ZK. But actually, if you are familiar with some of the techniques in blockchain, you don't need ZK. For example, if you only need to keep the secret for once and then review it, you can use commit review scheme, right? So hash it and then review it later. Okay, so that's one thing you can do. So that's one thing that you need to confirm before you even need even start developing your ZK app. Okay, so let's say you confirm that you need ZK for whatever application that you're writing, then most likely, at least for now, you need to learn a new language, okay? And the new language could be basically some DSL, domain-specific languages like Circom or Leo, etc., etc. Most recently, you can also write ZK circuits in Rust, but most likely, you're going to learn a new language. At least it's not done in Solidity. Okay, and then actually, each circuit needs some kind of a setup. Okay, so this is the nitty-gritty thing, but it's actually quite important. I don't know if anyone have heard of the KZG ceremony of Ethereum Foundation. There's like a page where everyone just go in and play around with the cursor, and basically they contribute some randomness to this kind of ceremony. So essentially, this is called a trusted setup. So a trusted setup is, let's say each of us give out a random number and we've all put it in a pool, okay, in a setup. So this is to ensure that unless the hacker knows every single one of our number that we give out, otherwise they can't really break our ZK proof, okay? So they need to know every single randomness that everyone contribute in the world. So the bigger the setup ceremony, the better. In the Ethereum one, I think there's like 80,000 people joining. So you need to know all the 80,000 randomness in order to break the system. Yeah, and then the rest of the things you should be familiar, which is then you of course also need to write the smart contract, build the front end, etc., etc., just like a normal DApp, right? So the right-hand side is just like the normal DApp. The left-hand side is the additional part that you have to write about ZK. Any questions so far? Oh, well, if there's no question, then let's dive into some application. Okay, last note on trusted setup. If you don't know what these words means, it's totally normal. The idea is just that you will see these words quite often if you start working in ZK. And the idea is just that there are a lot of proving systems. Okay, and each proving system basically have its own trade-off. Okay, so this is just two of the most common one. But the idea is then you also have to learn about all the trade-off. It's like using different backend, you know? Using different backend, choosing your backend has different trade-off, so that you will have to choose each of them and see like which one is the most suitable for your application. Okay, but other than that, I'm pretty sure 2 years later, no one is going to use these schemes anymore. So don't get into the names, but just remember that you have to think about like which backend to use for your ZKP all the time. Okay, right. Okay, as promised, application. So before I go into ZKML, let's talk about some more common application that you probably have seen. So the first one is about scaling, which is all the L2. First one is you can probably do signature aggregation. So I don't know if anyone has used multisig or Gnosis Safe or have heard of those before. Okay, yep. I guess most of the companies, right, at least if you're working on some kind of project, you have multisig. There's a limit on how many multisig signatures you can actually put on Gnosis Safe. I don't know if they have extended it, but I think it was like 16 or something like that. And that's because as you aggregate the signature, the call data gets huge, right? And that doesn't get accepted into the smart contract. But then, what if we can use ZKP to aggregate the signature? Then we can essentially have multisigs of 50 people, 100 people, 1,000 people. Well, I'm not sure why would you need that, but at least that enables it, right? So that breaks the limit of the smart contract. And that's the purpose of, one of the purpose of using ZKP on blockchain. And the other one is ZK rollups. Okay, so ZK EVMs, layer 2 systems. Again, I just want to mention that just because it has ZK in the name, it's only used for scaling. It's not used for privacy, okay? So ZK rollup doesn't give you privacy. So that's the first major area of application. And just some of the typical ZK EVM, just really for demonstration. I'm not going to go through this. But you can see that basically these are the a few of the big players in the ZK EVM space right now. And they all use ZK for the succinctness, the compression part. okay? Second major area of application is privacy, okay? And that's actually where my passion is I really want to do all the privacy-related application. Some of the ones that you might have heard about is mixers. So we'll give some examples in a bit. So mixers is essentially where people can hide their identity by mixing with a bunch of people. Okay, we'll see a more concrete example in a bit. Or decentralized ID. Okay, so this is one thing that you might have heard a lot about, especially with the Polygon ZKID already rolled out, which is essentially the same thing, the same technology that they're using. Again, it's to find a group of people that is similar to you and hide you within a bunch of people. So for mixers, perhaps the most famous application is Tornado Cash, which is now sentient, if you haven't heard of it. Essentially, for Tornado Cash, it will be, how it works is each of the person who uses the Tornado Cash put in exactly 1 ETH, or exactly 10 ETH, or exactly 100 ETH into Tornado. Okay, so now your identity is mixed with all the other people. And then you get your other address and then submit a proof to say that I have deposited 1 ETH before. But then you are getting that 1 ETH out with another address. Okay, so imagine if it's 100 people in, 100 people out, that's like 10,000, well, not exactly 10,000 combination, but you get it, around 10,000 combination, right? So that makes it very hard to track which account is related to which. So that's the idea. So that's the first kind of most used application in practice. Tornado Cash, similarly, there's something that is actually developed by the Ethereum Foundation called Semaphore. The idea is the same, but this time we don't use it for money. We use it for signal broadcasting. Okay, so you can imagine, for example, for a DAO, okay, so a group of people in a DAO, they can all join this so-called Semaphore group. Okay, so then now they are hiding their identity among this DAO. Each person gets maybe 1 vote. Okay, so when you're casting the votes, all they know is you're from this DAO. Okay, nothing else. So they don't know which address is coming out from. And in fact, this is used quite often right now and field extended. So, for example, Nouns DAO, the one with like the Noggles, Nouns DAO is having like a private voting proposal, working with a bunch of companies, trying to build private voting for their users as well. So private voting is a huge thing in DAOs, and that's one of the techniques to do so. And then there's a bunch of derived application that you can use with Semaphore. For example, you can build your reputation system, like everyone that has like 10 stars on GitHub goes into the same group. And then you can cast your votes based on your reputation. Or Twitter. So a CK version of Twitter would be, let's say if I know that I am reputable on GitHub, I can all join into the same group, right? And then I can basically tweet anonymously. Right, so all the people will know is that I come from a group that is reputable on GitHub or reputable on Twitter, but they don't know who I am, okay? So this is a version of like CK Twitter, and then you can use it for voting, etc. Okay, so a note is that to make the best use out of these applications, the key is actually to have a large anonymity set, right? So it all depends on how many people is in that group together with you. If there's only 2 people putting money in and 2 people getting out, that's not anonymous, because there's only that much combination, right? There's only 2 possibilities. So to have more than, 2 or a lot more than 2, be it 10,000, 100,000, that's the key to use this kind of application. Okay, so actually these CKPs all use the same type of circuit, which is called a Merkle proof. So in my opinion, sorry for all my teammates that have worked on this, but I think it's pretty boring. So actually, if you look at each ZK project, each new ZK project, and then you take a look under the cover and see what it actually does, most of them are doing a Merkle proof. Okay? So it's important to know that, but it's not useful for ZKML, which we'll be talking about in a bit. But it's important to at least know what is a Merkle proof. Okay? So if you have some computer science background, you might at least know what is a Merkle tree. Okay? Which is really a hashing data structure that allows you to, hash a bunch of number, right? So hashing, and then you get to a root. And then you can use this root to represent basically all the data that's under it. Okay, so this is a Merkle tree. So what is a Merkle proof is that, well, imagine now at the lowest level, these are all the people that have deposited 1 ETH, okay? So H3 has deposited 1 ETH, H4 has deposited 1 ETH, etc., etc. Okay, when they want to get the money out of Tornado Cash, for example, what they need to submit is these 4 numbers. Okay, so they only need to prove that they are part of the tree by submitting the relevant proof, so the relevant path. Okay, so for example, for H3, you can hash it to get H1, but then you also need H2 to go with it, and then you can hash it to get H0. Okay, so this is called a Merkle path. So in essence, if you have this, then you can prove that you're part of the membership. Okay, but Merkle proof itself is not ZK. In fact, Open Zeppelin has if you know about NFT airdrops, you can use Merkle proof for NFT airdrops as well, right? However, you can also put this whole thing into a ZK proof so that it even hides all the information in between, right? So if I have this 4 number, of course I know it's from H3. There's nothing zero knowledge about it because I know exactly where the path goes. But the key is I can actually hide everything with ZK proof and only shows that I have some number that goes to the root, okay? So this is called a membership proof. Just prove that you're part of the tree. And that's how most of the ZK applications nowadays relies on. Okay, so a Merkle proof. So yeah, so that is, I think if you know what a Merkle tree is, it should be quite easy to understand what a Merkle proof is. Great. So, well, finally, then we get to ZKML. So that's a huge, long introduction. I'm sorry for those who already know ZKP. But the idea is that, well, Merkle proof is useful for a lot of applications, but building custom circuits is also useful. So especially, building custom circuits can allow us to have some applications in outer space, such as zero-knowledge machine learning. So, well, how to understand zero-knowledge machine learning in particular? You can think of, let's say, we have some model, okay? So forget about the word circuit. We have some model, which is a neural network, that performs some inference, right? So a neural network, for example, ChatGPT, okay? ChatGPT, it will take some input data. It also has some model weights, and then it will give us some output. Right? That's just how every single machine learning model works. Okay, so for zero-knowledge proof, it wouldn't be useful if we hide both the input data and the neural network. Why is it not useful? Well, if I hide both the input data and the neural network weights, then I'm just telling you that I have some model that does some computation, and here's the result. Okay, that's not useful at all. So we have 2 scenarios, actually. So we have to expose some of the information. 2 scenarios. Either you have private input data and public model. Okay, so for example, you can think of it as, for example, I have a circuit that does face recognition, okay, for example. Okay, so then, well, in order for me to trust that it's a very good model, I need to expose the model weights. So I need to know that it's a good model because like 95% accurate, okay, with the model weights. And then now I will have my face recognition model I'll put my face, my picture into this face recognition model. And then output, for example, I don't know, my age, my gender, etc. Okay? And that I want to hide the input because I don't want everyone to see my face on the internet, right? So now, what I can tell you is that I have used this very credible model to prove to you that I am, first of all, I'm a human, right? And then I'm a female. I am several years old. Okay? So this is one possibility that you can do with ZKML. The second one is the other way around, okay? I have some public data and I have some private model weights. Okay, so what is that gonna be good for? So I don't know if anyone come from the AI or machine learning space, but there is this famous platform called Kaggle, which you can basically companies will post their data out, and then you're supposed to build a model for that data, right? And then the only way for you to get the prize is actually to submit your source code, because only by running your source code, then they can know that your model is 95% accurate, 98% accurate, etc., etc. Well, what if we actually am able to hide at least the model weights, maybe not the architecture, but the model weights from the bounty provider, right? So instead of giving my whole source code to them, I just give a ZKP. I just give a zero knowledge proof of I have this model, I have some hidden weights, but then you know that it's going to give out 95% accuracy, right? So I put the whole data set through my model and give out all the model output. So you can check the result. The only thing I'm not giving you is the weights. Okay, so this is one application that you can do. And that is also kind of one direction of research as well. Right, then, well, these two scenarios, what is it good for? Well, it could be good for multiple things. So for on-chain application, it can be good for on-chain trading model. So I know that there's actually some trading model going between like the Cosmos ecosystem and the Ethereum chain. And right now, how people doing it is they trust like a relayer in the middle to do the interoperability, right? So for you get like, for example, some trading model result on the Cosmos side, and then you're supposed to have a one person that relay that information to the Ethereum chain, right? So what if we can have a trustless way to do like all these AI models? So that's one thing. Or as simple as what if we can have a biometric authentication for a smart wallet, right? So let's say I have a very good model for fingerprints or for face recognition. I can do that and then have my smart wallet, which is a verifier contract, to prove that I own some fingerprints or to prove that I own some face ID. Okay, so that's one application as well. And also, you can have a lot of different tools basically running AI on Ethereum, even though the smart contract doesn't allow it by its size, right? Because now you can run it off-chain and then just submit the proof on-chain. So that's the on-chain application. For off-chain, there's actually a lot of things you can do as well. So for example, outsourcing inference computation, right? So I have some data. I really want to run a model through it, but I don't have the GPU to do so. If I want to give the data to someone else, I also want to make sure that they run the computation correctly, right? It's not just like, okay, I upload the data and they say they run it. So I need a source, I need a verifiable way to know that they actually did what they promised to say. So that's one way you can use it off-chain. And also benchmarking, so measuring model performance. That's also one of the application, kind of like Kaggle. How do I actually believe that you have certain models without you handing it over? So that's also one thing. And also proving model training correctness. So this is something that is really in progress right now, is that can we also do decentralized model training using ZKML? Okay, so just to kind of wrap it around and at least this is a hacker house, so I realized I should mention some of the tech stack as well. So actually, I kind of just say that, okay, we can put a neural network into a ZKP circuit, but in reality, it's not that simple. In particular, there's two challenges. So the challenges is, first of all, ZKP circuit is actually fixed point, in particular integers, okay? Whereas all our neural network actually exploit on the fact that it's floating point, right? So you have all the gradient, all the weights is actually floating point. So to convert floating point to fixed point, there's a kind of a trade-off there. And also model size, okay? So just to kind of credit all my fellow ZKMLers in the past 2 years. So actually 2 years ago, this is the first time we have seen ZKML, which is just linear regression, okay? Which is already useful for a lot of application if you think about it. A lot of the real world thing we can actually use linear regression to achieve. But that was the first kind of starting point 2 years ago, okay? And then 1 year ago, there's actually a group saying that they did a neural network on MNIST. So for those of you who don't know, MNIST is a bunch of handwritten digits. So it's a toy data set for machine learning, for computer vision. It's a bunch of like black and white numbers, okay? And for 1 year ago, they kind of cheated. They didn't put the whole neural network into a circuit. They just put the last layer, okay? So the whole layer is public until the last layer. So that's the 1 year ago. And then we fastly advanced to putting a whole model onto a ZKP circuit. And then actually, we also started doing AI art generation circuit. And then 2 weeks ago, there is a group that claims that they can do 100 million parameters of models onto ZKP. And then also last week at the ZK Summit, Daniel's group said that they can actually run GPT-2 on a ZKP circuit. Okay, of course it's huge. Okay, just saying that it can run doesn't mean that it runs on your laptop. In fact, you actually need 1 terabyte of RAM, I believe, to run the GPT-2 as a ZKP circuit. Okay, and then also last week we also start experimenting with other machine learning models, right? So that goes back to the challenges where, you know, the current neural network paradigm doesn't really go with these 2 challenges here. In particular, the fixed point and the integer part. So actually, beyond neural network, there's a lot of other machine learning paradigms out there that is less discovered because of the whole neural network hype for the recent years. So for example, there's something in the 70s called the weightless neural network, which people actually use to recognize fingerprints. Okay, and that should be quite CK friendly. There's a lot of things that is way more CK friendly than a lot of other like floating point models. So just to kind of like see the trend of really transforming over a lot of the past 2 years, really. Right, so that's the kind of wrapping up the last bit of my talk. So this is kind of a POC that I've built before, just to kind of let you visualize how you can potentially build a CK Kaggle. I call it C Kaggle, just to write on the word. So the idea is that, well, how would a Kaggle look in a decentralized point of view? So you have some companies posted a bounty. Essentially, they will split their data set into public data and private data, just like the normal Kaggle. This public data is used to train a model in Python. And then there's this toolkits that I've built that basically translate your model also then into a CKP circuit, okay? So this is already done by many groups. You can transform a Keras model, you can transform a TensorFlow Lite model, you can also transform a PyTorch model. So that's already done. Okay, once you have that model, basically you submit it for a verification. And you submit the proof to the verifier contract. Right? And also, at the same time, while you submit the proof, you also encrypt your model to be submitted as well. Right? The reason why you want to encrypt it is you want to delay when the bounty provider is going to get the model. Okay? And then once you encrypt it, at the end, you also check your model with the private data. So once everything checks out, the accuracy looks good, the verifier say yes, it's a valid proof, then at the end, you release a bounty. Okay? So this is a kind of a high-level diagram, but in essence, you can think of it as at least 4 to 6 transactions back and forth in a way. So it's a little bit like an escrow contract, really. So you're putting down your model, kind of putting down a bid, and then there's a bunch of verification going on before releasing. So when the bounty is releasing, then the person also gets the decryption key to decrypt your model. Right? So that's how it's done. And at least there are 3 major components, which is you have kind of a circuit library that does all the common operations in machine learning. You have a transpiler, which converts the machine learning model to circuit. And then you have, the actual platform, which is a DApp, right? So it includes all the smart contract, etc. So this is already a proof of concept on my GitHub, which I will link to later. Right. So that's kind of just a proof of concept what can be done. Of course, right now, the model size is still pretty small that you can try to fit on it. Right. So if anyone is more interested in the previous project, here's the more detailed write-up if you really want to check out the details. It's not too technical. It's more of a description of like the development process and etc. Okay, right. So since we're at a hacker house, I might also mention all the tech stacks that you can possibly need for ZKP. So Circum is one of the more, I guess, basic language to write circuits. This is one thing that you will see often when you're starting out. It has like an option to prove with different proving system, and also most importantly, export as a verifier smart contract, which some of the circuit language actually don't. Okay, so this is one thing when you want to, if you really want to have an on-chain verifier, this is probably the language to go to. Cairo, which is the language for Starknet, is a more general purpose Turing complete language. It might not necessarily provide you privacy, okay, unless you actually know what you're doing. right? So you can do a lot of things on StartNet with Cairo without privacy, okay? Just because you're coding on StartNet, just because you're coding on Cairo doesn't mean that you're writing ZKP, okay? So be careful of that, but you could. At least with Cairo 1, I think you could. And then there's also Rust, which is, there are quite a few libraries to do so, like Halo 2, Plonky 2, etc. These usually have the latest proving schemes, so it's the fastest. The problem is, first of all, you have to be familiar with Rust itself. You also have to be familiar with something called a Plonkish arithmetization, which I'm not going to explain here. But in essence, you're no longer writing even a program. You have to lay out your circuit in a way that fits like their arithmetization. So that's again, I think in here it's kind of like a, well, from here to here is an increase in difficulty level. Let me put it that way. Right. So that's, but the important thing is also that's where the most exciting things usually happen, is in the Rust language. So that's the tech stack. Right. And so how do you actually get started if you want to write ZKP? So these are several kind of more introductory, well, I wouldn't say 0xPark and ZK-Hack whiteboard series is necessarily introductory, but they are all very good resource to start through. There's a lot of tutorial on 0xPark. This is actually an open source course that is built by me, focusing more on the applied side. And if you want to have a kind of, if you like videos more, then the ZK whiteboard session is perhaps the channel to go to. Cool. So just to credit all the projects that I've mentioned so far, in case you want to check out any of them, and here's the projects that I've mentioned so far. So I think it would be a good time to take questions. If anyone has any question, doesn't have to be the talk related, can be anything ZK related, can be anything you heard about and be like, I don't understand what that means. Yes, correct.
So when you then you combine them, proving the change very fast.
Correct, yes. So all the so this part is in Python, and then you put it in the circuit. Before you submit it, actually you also do the computation of the proof of chain. So you just submit a result. So a circuit, you can think of as a list of operations that needs to be done to the data. So why we don't call it a program is because those operations are quite limited. So you can only do addition and multiplication up to quadratic terms. Right, so that's why we call it a circuit, not a program. But yeah, but you can think of it as a program that you write for ZKP. A simple one, yeah, basically. A bunch of operations that you need to do. Yeah, go ahead.
Yeah, you mentioned about the back end. We consider like Grok 16 and Flonk. And you mentioned that they are popular now, but you think in the future there are not going to be that much projects that can use these like scheming.
Right, so that's a very good question. The funny thing is I'm actually not a cryptographer, so I'm not very familiar with it as well. I think for us, as if you're writing an applied ZK app, most importantly is to understand the trade-off. So when I say it's going to phase out, that's just because there are some benefits to it. Okay, so for example, actually Polygon ZK ID still use Growth 16 if you look at their tech stack. But the idea is, as I said, Growth 16, you need a trusted setup for every single circuit. So imagine you have to invite a bunch of people to contribute randomness every single time. But what they get is small proof size, which means the verification is very fast. So how Polygon ZKID actually does it is they have some very generic circuit to prove identity. In fact, I think they only have 3 right now. So if they only have 3 kind of identity proof, then they can do a trusted setup at the beginning. But that also means you can't add new types of identity, basically. Because if you want to add new types of identity, then you have to do a whole trusted setup again. Yeah, so so I think when I say it's going to move away from Ponk, it will mostly be moved away from these, but not the whole Ponkish scheme. So the Ponkish schemes is pretty much where everyone is looking at right now. So I think the reason why everyone is looking at it right now is probably this second property here, where you don't need a setup or even no setup. So that's why people have been looking at it. It's also way more efficient, actually, than actually writing a circuit. So in this case, they are arithmetizing a circuit instead of writing a circuit itself. So that's why, the second one is becoming more and more popular. But that's not saying that the first one is not used. Actually, it's still used in a lot of places.
So it seems like you need to write a new circuit for each machine learning algorithm. So is that possible, like for one circuit, including like several machine learning algorithms?
Yes, but no. So even for different sizes of CNN, like the different convolution size, you actually that parameter there is already a need for a new circuit. So that's the annoying part. It's not saying that it's impossible. So if you use like this Plonkish scheme, what you can do is basically trying to fit all the machine learning model into like one giant, what we call lookup table. Okay, so instead of just computing everything is a lookup table. Then essentially you could do multiple different machine learning models over there. But I'm not sure how efficient that would be. So yeah, so the idea is still, at least for now, for each model you have like one custom built circuit for it. No, not yet. So I have the benchmark for example, a weightless model versus a weightful model. So a neural network versus what I say the 70s when they use weightless model. That is 5 times less efficient than like convolutional model. So for every lookup table, you have 5 times more parameters than the convolutional model, at least for now. So yeah, but there are more benchmarks that we'll be doing. Yeah, but in that case, what they have is, so for ECKL, what they have is a transpiler that transpile the ONNX, which is the PyTorch network graph, to a circuit. But it's still a different circuit. Like it's a transpiler, which helps you easier to get a circuit, but it's still a separate circuit for each model. Cool. Well, if there's no further question, I don't know if any one of you are into POEP collection here. But I do have a POEP that I have here. Hold on. Let me get to that part. I'm not just doing a POEP for POEP's sake. So the idea I thought was that it's actually quite difficult to maintain contact afterwards. It's like, yeah, you got my Twitter or something down, but you don't really remember how to find me because you don't know my username, etc. So I thought POEP could be a good way to let you recall that, okay, you have heard about this ZKML talk in April 2023, right? So you just go to your POEP and scroll to April 2023 and then find me. So I haven't given out a lot of codes, but I don't know. If any one of you actually collect POEP, you can go ahead. But yeah, so inside the POEP, other than the arts, you also get a link to my link tree, which includes all the GitHub repository that I have, or my Twitter, or my Telegram, so that if anyone wants to find me to talk about ZKML, you're welcome. You might have to, because they don't really support multi-scan, so you might have to scan more than once if you guys clash. That's the bad thing. Luckily, we only have around 20 people here, but otherwise it will be pretty annoying. Great. I will take any last-minute question if there's any. Otherwise, that would be the end of this talk. Thank you.